We're now ready to apply this, this methodology to linearize our full equations of motion. Now this section has a lot of equations. I've typed them out here to save some time so we're not writing things down. And the important thing to remember as we go through this is just to realize what we're doing kind of from a larger perspective, okay? And so anyway, by the end of this, we're going to end up with some equations that look very different than the original equations of motion that we're used to. Not horribly different, but a little bit different. And I just want you to understand how we got there, okay, starting from these, from our traditional equations of motion. So what I have right here is our current equations of motion, okay, the top six, remember, that's Newton's second law, F equals ma. And then the bottom six are the kinematic transformation equations. Now the top six can be written a little bit differently. This is identical to this. We've just moved W of G over to the left-hand side and our inertia matrix back over to the left-hand side. And actually this is how we originally developed it, and then we kind of rewrote it this way, but we're going to actually go back to this form as we work through this linearization process. But these are identical, okay? These six and these six equations are identical. It doesn't matter which way you write it, but we're going to use this form as we work through this. So the first step is to take each of our parameters within our equations of motion here and write them as a parameter at our known solution or a particular solution plus a deviation in that parameter relative to that known solution. Okay, so for example, our u velocity is u naught plus delta u, v is v naught plus delta v, w equals w naught plus delta w. We can do the same with pqr, x, y, z, phi, theta, psi, and then our forces in our body fixed coordinate system. So these are fx, fy, and fz. Our weight vector, and this is where we're going to come back over here and use this form of this equation. So wx, wy, and wz. And then our moment vector, mx, my, and mz. And then also, these forces and moments we're going to see are a function of our control surface deflections, our aileron, elevator, and rudder. And in order to trim the aircraft at our known solution, we've got these known values, and then we're going to look at deviations in each of these control surface deflections. Now, as we walk through this, the book I'm following is Phillips's Mechanics of Flight, second edition, and he actually drops the thrust. It seems to me like you should also include a thrust term here, so you'd actually have four variables down here. But we're not going to include that here. It's actually not going to affect the outcome, at least for what we're going to use these equations for. So it's not a big deal for us, but I think in general you probably could include a thrust term here because that's another control input from the pilot. So anyway, so just so you know, that's not going to be in this development. Okay, so at this point, before we plug these all into these equations up here, we want to choose a known solution. And we're going to choose a known solution that is, so this is our known, our particular solution. We're going to choose this solution to be steady flight. Now, I think in the previous video, I said steady level. We're actually not going to require it to be level, okay? So we're going to require steady flight with zero side slip. So that means that beta equals 0. We're going to have 0 angular rates, so P, Q, and R. And because of this, we can also choose our coordinate system here a little bit. So we're going to align the x-axis of the aircraft with the direction of flight, okay? So that's going to simplify things just a little bit, because that means that u is equal to v naught, so we're traveling at some capital V velocity, and we're just going to orient the x-axis of the aircraft in the direction of V naught, or we're just going to define the x-axis of the aircraft, I should say, in the direction of V naught, okay? And one last thing is that the dynamics of this aircraft do not depend on the direction of flight, whether we're flying north, south, east, or west. And so just for simplicity's sake, for this phi term here, to see our the direction of flight, we're going to say that phi equals 0, okay? Excuse me, not phi, psi. Psi equals 0, so we're going to align the aircraft so it's flying due north because the dynamics shouldn't depend on the direction of flight. Okay, so with that, we can actually drop a bunch of these terms in here. So let's just walk through here. So we're going to say that u equals, or excuse me, this u over here, I made one typo here, u naught equals v naught. So that means, remember, we subscript things with naught when we're talking about that known particular solution, and these are also p naught, q naught, and r naught, okay, and psi naught. Here we go. So those are at our known solution. Those are the known values, okay? So if that's the case, then at our known solution, V naught is actually 0 because we say that beta naught equals 0, right? We're saying that our known solution, we have no side slips, so V naught is 0. Also, because we've aligned this little u, or our x-axis, with the direction of flight, our W naught is also 0. And then we can walk through, so P naught, Q naught, and R naught are all 0 because we said that our rates are 0. And then phi naught, our bank angle, we're going to say that that's 0. So we're looking at steady flight without any bank angle. And then psi naught is 0 because we're aligning our aircraft with due north for our trim condition. Now, theta naught can be non-zero. I'm just going to circle that there. That could be non-zero because we said steady flight, but that actually could be steady climbing flight, okay? So we're going to allow theta naught to be non-zero if we like. And then in this condition, that requires that our force in the y direction is 0. Also, our weight in the y direction is 0. And the moments about the origin are all 0 because we're in a trim state, okay? Now, another thing that we could work out with a free body diagram here, but I'm just going to write it down, is that Fx b naught, so our force in the x direction. Now, remember, Fx is our pseudo-aerodynamic force. That includes the aerodynamic force plus the thrust from the aircraft. In this trim state, it has to be equal to minus wx b naught. So it has to be equal to the weight vector in the x direction, and that's the same with z. So fz b naught is equal to minus wz b naught. Okay, so the aerodynamic, or the pseudo-aerodynamic force here that includes thrust has to offset the weight in the x and z directions. Okay, so if we now take this information and plug it, so we would take all of this with all of this here and plug it into this equation, and then and drop out all of these terms that are 0, what we get is an equation that looks like this. Now this is just F equals ma, so for a minute we're just gonna we're not going to look at these kinematic transformation equations. Okay, we'll come back to that in a minute. So we're just looking at these 6 equations here, F equals ma, and all of that simplifies to this relationship right here. Okay, once we plug in all of these values, many of them drop out because they're 0. Another thing that we've dropped actually to get to this point is any second order terms. So let me show you what I mean by that. So for example, let's look at these terms right here. So R, if we come down to our definition of R right here, we've got R naught plus delta R, right? So that's what we're going to plug in for R right there, but R naught is 0. And then that's multiplied by V, and so we're going to multiply that by V naught plus delta V. Well, V naught is also 0. So when we multiply these together, R times V, what we actually get is a delta R times a delta V. Now remember, in the previous video, we talked about, for small disturbance theory, to linearize these equations, we're going to drop second order disturbances, okay? So this is a second order disturbance because we have a delta R times a delta V. Remember, these are deviations from our known particular solution. And so we're saying that deviations in R and V are both small, and when we multiply them together, then they're extremely small compared to the other things in this equation here, okay? So that's why the RV would disappear. Now, R times U actually will not disappear, and that's because when we have R, when we plug that in, we've got a delta R that shows up multiplied by U. Well, remember, U is equal to U naught plus delta U. Well, U naught is non-zero, right? So V naught and W naught were 0, but U naught is equal to capital V naught over here. So when we plug that in, you can see that term show up right here. We're going to get a delta R times a V naught, okay? So, anyway, these are simplified equations somewhat. These are linearized equations, or at least the first step along these lines, once we've plugged in these terms and dropped second order disturbances, okay? So we end up with these equations here. Now notice that this vector here is our change in, or our disturbance. That's what this capital delta means. It's our disturbance value, right? So we've got our total value is equal to some nominal value, or the known solution value plus a disturbance from that. And so what we end up with here in this vector here, which was UVW PQR, once we plug in these equations here and set our nominal values, many of them to 0 or whatnot, then we end up with a vector here of disturbances, actually, instead of the actual value. So this is a vector of deviations from our known solution, okay? And these deviations, or the change in those deviations, is related to these other things, as we've, straight from these equations right here, okay? Okay, so the next thing we're going to look at are these delta force and moments over here. So these are aerodynamic forces and moments, and these are deviations from our force and moment at our known solution, okay? So these are just deviations from that, and we're going to use Newton's method. Not Newton's method. We're going to use a Taylor series expansion, to write the first derivative of each of these with respect to parameters that we know they depend on. So we know that the force and the moment depend on these things. They depend on the UVW, or our velocities. They depend on our rates, PQ and R. They depend on our accelerations, or they can depend on the accelerations, U dot, V dot, and W dot, translational accelerations. And they also depend on pilot control inputs, delta A, delta E, delta R. And again, this is where we would include a throttle setting or something if we wanted to, but we're not going to include that there. So what we've done is basically we're writing these forces of moments, or these deviations of forces of moments, as functions of just the first term in the Taylor series. So for example, if we just take this first line here, the change in force in the x direction is equal to the first term in the Taylor series of the change in force in the x direction with respect to u times delta u, the change in the x direction with v multiplied by delta v, and x with respect to w times delta w, right? And then we can do the same thing over here for p, q, and r, the same thing for u dot, v dot, w dot, and the same thing for delta A, delta E, and delta R. So that first equation there is just a Taylor series expansion where we've only retained the first term because we're neglecting the higher order terms because we're trying to linearize this whole system of equations. Okay. Now, so these look kind of nasty. We could do the same things for the moment. They depend on the same variables here. But it turns out that a lot of these actually go to zero on the basis of symmetry. Okay, so we're going to assume that our aircraft is symmetric. And actually, we've already done that from our inertia tensor from these equations that we started from. We had already assumed that the aircraft was symmetric. And if the aircraft is perfectly symmetric, then many of these terms actually drop out. So, for example, let's look at this term right here. This is a change in the x force with respect to v. So the force in the x direction very well can actually be a function of v. So if we were to plot it, so this would be the force in the x direction in the body fixed coordinate system, and then on the x-axis would be v. So it will depend on v, but if the aircraft is perfectly symmetric, then a positive v, and v is related to beta, so that's probably easier to think of. If you have a positive beta, so for example, first of all, we've got some nominal force here when beta is equal to 0, right, in the x direction. And then if we increase beta a little bit, then we'll get some change in the force due to that change in beta. But if the aircraft is perfectly symmetric, then changing it to negative beta will actually create that same change in force, okay, in the x direction. And so so when we take the derivative of fx with respect to v at our nominal condition, the derivative there is actually 0, okay? And so on the basis of symmetry, we can drop out a bunch of these terms, and then there are also some that I can also point out. For example, this next one, so that guy's 0. This Fy with respect to u, let's talk about that for just a second. That's a force in the y direction. If you have a change in u, which is your forward velocity, should that change your y force on the aircraft? Well, no. If your aircraft is symmetric, then a change in u will not affect the y force. So that's why that turns out or drops out. So I'm just going to put a slash through these terms that can be dropped out based on symmetry of the aircraft and symmetry of the aerodynamics because the aircraft is symmetric. Okay, so all right, so we're just crossing each of these out. That would be 0 on the basis of symmetry. You can see a whole lot of them drop out here, okay? Now, what I've done is I've left these two matrices that have to do with accelerations, just because, now, we're going to do the same thing here. Many of these are going to drop out. But there's also, I guess, one other thing to know about acceleration. So first of all, you may have been a little surprised that we included this. The reason that we have to include this is because if for example, there's a change in W, okay, so we're flying along and we have a change in angle of attack, it takes a finite amount of time for the change in vorticity on the main wing caused by that change in angle of attack to propagate downstream and affect the lift on the horizontal tail. And so that means that the pitching moment, because the downwash is changes as a function of time, the pitching moment is also going to change as a function of time, which makes our forces and moments on the aircraft sensitive to accelerations, not just to our actual velocities, but also changes in those velocities, okay? And we'll talk more about that later, but that's why we had to include these terms here. Now, if we assume that a change in side velocity doesn't really, or that our aircraft is not really sensitive to changes in side velocity, then these three can be dropped out. And then just based off of symmetry, you can drop out these other ones here. Okay, so we drop those out. So anyway, you can see that a whole lot of these terms have dropped out based off of symmetry of the aircraft and also symmetry for the aerodynamics. Okay, so we've talked about these forces, and we now have a Taylor series expansion of these forces here. And let me just write that here. So this is the Taylor series expansion, including only linear terms. Okay, that's what this is here. Okay, so now let's go back to this set of equations up here. Another thing we want to look at is this change in the weight as a function of, as a function of orientation. Okay, so this change in weight, or this is the deviation in our weight vector as a function of our orientation. Now, the equation for weight is right here. So we came up with this previously. The weight in the x, y, and z directions depend on how we are oriented. Our elevation angle here, theta, and our bank angle here, phi. So our delta, we're going to do the same thing here. We're going to take the Taylor series expansion of this weight vector to get the derivative of the weight vector, or the change in that weight vector. So if you take the Taylor series expansion, taking only first derivatives, and then multiply them by our deviations, right? So again, this is just the Taylor series expansion. From the previous video, you should recognize what we're doing here, but we've got a delta in our weight vector is equal to just the first term in our Taylor series expansion multiplied by the deltas, or these deviation values. And so let's just look at this first term here. The change in x with respect to phi. Well, if you do the math here, x does not depend on phi, and so the derivative is 0. If we look at this next one, the change in x with respect to theta. So if you take the derivative of this with respect to theta, you get the cosine of theta here. So we've got a minus w times cosine theta. Now notice that we've subscripted this here with knots, because what we're doing is, remember, these derivatives, we compute these at the nominal condition, or at our known particular solution. Okay, so we look at the derivative here, we get the analytic derivative, but then we evaluate that at the known solution. So that's why we've got the knot here, because we're evaluating now theta at our known solution. And of course, our weight doesn't depend on psi, and so that's why this last column is 0. Okay, so we've gone through a whole bunch of stuff here, but basically, if we take these values now, so we've got this delta weight vector, which we've got over here. We've got delta forces and moments, which a bunch of those drop out here. If we plug all of that back into this equation here, then that's going to give us our linearized form of F equals ma. Okay, that's our Newton's second law. That came, remember, from our original nonlinear equation of motion. So that's now been linearized. We can do something very similar with our kinematic transformation equations. Now, I'm not going to work through that, but you follow a similar process of looking at these Taylor series expansions and also plugging in these types of things here, where we're looking at deviations relative to our nominal flight condition. And anyway, you walk through the same process, and when we finish, we have now a total of 12 equations that have been linearized. Okay, and the really cool thing about that, maybe I'll stay up here for just a second, is that so originally in our nonlinear system of equations, these were highly coupled. So meaning between longitudinal and lateral. So meaning that so for example, u, which is a longitudinal term, depended on v, which was a lateral term, and r, which is a lateral term, and then v, which is a lateral term, depended on u and w, which are both longitudinal terms, right? So if we divide these up into longitudinal and lateral, our original equations were highly coupled. It turns out that once we linearize these and drop all of the small disturbances, or the higher order disturbances, and keep only the linear terms, it turns out that we can decouple these into actually two sets of 6 equations. So instead of having one set of 12 equations, we can decouple these into two sets of 6 equations, where the first is, and that's the first set here. So these are the linearized longitudinal equations. And these are the linearized lateral equations. Okay, so it turns out that once we do the small disturbance theory, the longitudinal equations can be broken apart from the lateral equations. They're independent of each other. We can solve these 6 equations independent of these 6 equations. Okay, and that's really powerful because as we get further along here and get estimates for things, we're going to find that these smaller matrices are much easier to work with, at least from an analytics standpoint. Numerically, we wouldn't care, right? So if we were to plug this into a computer, it wouldn't care if we're trying to solve a 6x6 or a 12x12 matrix. Computers today can solve either of those just fine. But when we're trying to study the dynamics of this and understand on a more fundamental level, it's going to be really helpful that we can divide these up into the longitudinal and lateral equations separately and analyze them somewhat independently. Okay, so these are now this is still F equals ma and our kinematic transformation equations. So the top 3 equations of each of these are F equals ma equations, and then the bottom 3 equations here are our kinematic transformation equations, but we've been able to divide them up because this coupling has the coupling has disappeared once we linearized these equations. Okay, so hopefully these final equations don't scare you at all. This is just a different form of our total equations of motions that were nonlinear. We've now linearized them. And in the coming video, and I guess I should say, we've rewritten some of these derivatives. This is kind of shorthand for these types of derivatives here. These are partials with respect to certain variables, and these derivatives now are the derivative of some value with respect to one of our variables evaluated at the at this equilibrium flight condition, or I should call it the nominal flight condition, or a known particular solution. Okay. So we're now going to look at how we evaluate each of these derivatives and relate them to things that we know about the aircraft. And then we'll plug those in and get our final system of linearized equations that we can look at in a dynamic sense.